Today we are going to discuss a long topic, heat and thermodynamics, including kinetic theory and waves and oscillations. Friends, today we are going to discuss a long topic, heat and thermodynamics. Very important topic. It is equally important for chemistry also. Then waves and oscillation. A few questions from waves and oscillation. First, some questions about heat and thermodynamics. Let's go through the first question. Question number 1. The expression for the kinetic energy of 1 mole of a diatomic gas. According to kinetic theory, several postulates are there, several equations are there. Then, by kinetic theory, the kinetic energy of 1 mole of an ideal gas is 3 by 2 RT, where R is the universal gas constant, T absolute temperature. Kinetic energy of 1 mole of an ideal gas is 3 by 2 RT. But based on the equipartition theorem, formula will be different for different gases. Then what is equipartition theorem? Let's go through the degrees of freedom first, then equipartition theorem, then its application to this equation. Okay. The number of independent variables or coordinates to locate a system or to represent the state of a system is called degree of freedom. And the degrees of freedom, number of degrees of freedom for a monatomic gas is 3, but for a diatomic gas is 5, and for a triatomic gas it is 6. At very high temperature, it becomes 7 for triatomic gas, that is 1 because of the vibrational motion also. That is, for a monoatomic gas, the number of degrees of freedom is 3. Then for a diatomic gas, it is 5. Then for a triatomic gas, it is 6. And at very high temperature, it becomes 7. That what is equipartition theorem? The kinetic energy, the total kinetic energy of a gas is equally distributed to each degree of freedom, and the kinetic energy per degree of freedom per molecule is half kT, or the kinetic energy per degree of freedom per mole is half RT. Here, the question is about 1 mole of a diatomic gas. For a diatomic gas, there are 5 degrees of freedom. Therefore, kinetic energy of 1 mole of an for 1 mole of an ideal gas, the kinetic energy is 3 by 2 RT. Then for a monatomic gas, also it is 3 by 2 RT. For a diatomic gas, since there are 5 degrees of freedom, the kinetic energy of 1 mole is 5 by 2 RT. And for the kinetic energy per molecule is 3 by 2 kT, where kinetic energy per molecule is 5 by 2 kT, not 3 by 2, 5 by 2 kT, where K is the Boltzmann constant, that's capital R divided by Avogadro number. Means the gas constant per molecule, that is Boltzmann constant K. Kinetic energy per degree of freedom per mole is, by equipartition theorem, half RT, and for kinetic energy per degree of freedom per molecule is half kT. Therefore, for a monatomic gas, K per mole is 3 by 2 RT. For a diatomic gas, K per mole is 5 by 2 RT. And for a triatomic gas, K per mole is 6 by 2 RT. Here, for a diatomic gas, the expression for the kinetic energy of 1 mole of a diatomic gas, the answer is 5 by 2 RT. That is that. Here, 5 by 2 RT gives the kinetic energy of 1 mole of a diatomic gas. Therefore, the correct choice is B. For the first question, the correct answer is B choice. Question number 2. The molar specific heat at constant pressure for a diatomic gas. First, I will discuss some important points about the specific heat capacity for gases. For gases, during the heating process of a gas, we keep either the volume or pressure as a constant, and hence for a gas there are 2 specific heat capacities. One, specific heat at constant volume Cv, and the other one specific heat at constant pressure Cp. Cv and Cp. But usually for gases, the quantity will be, it will be more convenient to measure in terms of mole instead of gram or kilogram. In terms of mole instead of in terms of mass. Therefore, if the quantities are measured in terms of moles, two allowed specificates are molar specificated constant volume and molar specificated constant pressure. Also represented by Cv and Cp, but we have to identify the exact meaning by observing through the units. If molar specificate is given, the unit will be joule per Kelvin per mole. Otherwise, it will be joule per kilogram per Kelvin. Instead of kilogram, mole will be given. If molar specificate is given, the SI unit is joule per Kelvin per mole. If it is not in terms of mole, that is ordinary specificate. If it is given in terms of mass, unit will be joule per kilogram per Kelvin. Now, here the question is, the molar specificated constant pressure for a diatomic gas. Here also equipartition theory is applicable. Actually, for a monatomic gas, Cv will be given by 3 by 2 R and Cp is given by 5 by 2 R. We have Cp minus Cv equal to capital R by May's relation. If Cv is 3 by 2 R, Cp will be 3 by 2 R plus R equal to 5 by 2 R. But equipartition theorem is applicable to this case also. For a monatomic gas, Cv is 3 by 2 R and Cp is 5 by 2 R. For a diatomic gas, Cv becomes 5 by 2 R and Cp becomes 7 by 2 R. And under normal conditions, for triatomic gas, Cv equal to 6 by 2 R and Cp equal to 8 by 2 R. That is, for different gases, different formula will be obtained for this Cp and Cv also. Here the question is, the molar specificated constant pressure for a diatomic gas means Cp for a diatomic gas is Cp equal to 7 by 2 R for a diatomic gas. Therefore, here the answer is 7 by 2 R. C choice is the correct answer. Now, question number 3. Diatomic gas is heated inside a cylinder with a frictionless piston. I'll draw the figure. A frictionless piston. Then pressure inside will be P. If heat is supplied externally, initially the heat energy is utilized only in increasing the internal energy. But after some time, it pushes the piston outward, then pressure inside remains constant. Initially, the heat energy is utilized only in increasing the internal energy and then to do an external work also. Here, the question is, fraction of the heat energy utilized in increasing the internal energy is, we have du by dt, use the internal energy, then du by dt equal to Cv and dq by dt, dq is the heat energy supplied externally, use the internal energy, du is the change in internal energy, dq by dt equal to Cp generally. Then du by dt, fraction of the internal energy utilized out of the total, that is change in internal energy divided by total heat supplied. Fraction of the heat energy utilized in increasing the internal energy means what is the value of du by dq out of the total given heat, how much is utilized for increasing the internal energy. Du by dq means equation 1 divided by equation 2. We have du equal to 3 by 2r, dq equal to 5 by 2r. Then du by dq equal to 3 by 2r divided by 5 by 2r for a monatomic gas. Here, a diatomic gas is heated. Here also equipartition theorem is applicable. Then du by dt Cv becomes 5 by 2R and dq by dt Cp becomes 7 by 2R. Therefore, for a diatomic gas, du by dt divided by dq by dt will be equal to 5 by 2R divided by 7 by 2R, means 5 by 7. 5 by 2R divided by 7 by 2R. Therefore, the fraction of the heat energy supplied which is utilized in increasing the internal energy is heat energy utilized in increasing the internal energy. That fraction is du by dq equal to 5 by 7. Therefore, here the correct answer is D, 5 by 7. Question number 4 is about heat engine, about Carnot engine. Heat engine is a device to convert heat energy to the mechanical energy. And the Carnot engine is an idealized heat engine which can never be made practical. Means under all the conditions will be ideal. Or under the ideal conditions, the concepts are derived. That is, all the heat engines must have a source, sink, working substance, cylinder and a piston and a platform to keep the cylinder. Here the source should have, source means a hot reservoir at a high temperature. But for a Carnot engine, it should have an infinite thermal capacity. Means we can accept any amount of heat from that source. It's an ideal condition. Then about the sink, cold reservoir of infinite thermal capacity means we can reject, or the sink can accept. Source can donate any amount of heat to the working substance, or the working substance can accept any amount of heat. But sink can accept any amount of heat rejected by the working substance. Source is a hot reservoir of infinite thermal capacity which can donate any amount of heat to the working substance. Sink is a cold reservoir of infinite thermal capacity, means which can accept any amount of heat rejected by the working substance. Then working substance taken inside the cylinder is ideal gas, means all the conditions are ideal. Here, Carnot engine, it is an idealized heat engine which can never be made practical. Different parts of a Carnot engine are source, sink, then working substance, that's the substance to be taken inside the cylinder with a frictionless piston. The side wall is perfectly insulated and the base is perfectly conducting. Then it needs a platform to keep the cylinder which is perfectly insulated. These are the essential parts of a Carnot engine. And the working substance absorbs some amount of heat from the source and rejects an amount of heat to the sink, doing some external work, Q1 minus Q2. Q1 is the heat energy absorbed from the source, Q2 is the heat energy rejected to the sink, then Q1 minus Q2 is the work done by the engine. Here, the question is about Carnot engine and different thermodynamic process included in a Carnot engine. First, the gas is allowed to expand under the isothermal condition, absorbing the heat energy from the source. Then, second stage is allowed to undergoes an adiabatic expansion. First, isothermal expansion. Second stage undergoes an adiabatic expansion. Then, compressed isothermally. And finally, compressed adiabatically. During the isothermal compression, a heat energy Q2 is rejected to the sink. Means the thermodynamic processes included in a Carnot cycle are: first one, isothermal expansion. Second one, adiabatic expansion. Third one, isothermal compression. And fourth one, adiabatic compression. Here, the choices are isothermal expansion, it is there. Second choice, adiabatic expansion, it is also there. Third choice, adiabatic compression, it is also there. Then A, B and C are correct. That is, the correct choice is D. Which of the following is or are included in a Carnot engine? Isothermal expression, adiabatic isothermal expansion, adiabatic expansion, adiabatic compression, A, B, and C. All these thermodynamic processes are included in a Carnot cycle. Hence, the answer is D. Question number 5. This is about kinetic theory of gases. Actually, 9 postulates are there. The 9 postulates, I will explain one by one. First one, gas molecules can be considered as rigid hard spheres. Molecules are in random motion. During their random motion, the molecules collide with each other and also with the walls of the container. The collision with the walls exert a new property called pressure. Collisions are perfectly elastic. Gravity has no effect on the gas molecules. The average kinetic energy is proportional to the average kinetic energy is proportional to the absolute temperature. These 7 postulates are correct postulates. Then the next 2 are proved as wrong later. 1. Volume of the gas molecules will be negligible compared to the whole volume of the gas. At low temperature and high pressure, it is wrong. Then, no intermolecular force of attraction or repulsion. These 2 are later proved as wrong. Other 7 are correct postulates. Totally 9 postulates are there. In the given question number 5, which one is proved as wrong later? First one, there is no intermolecular force of attraction or repulsion. It is a postulate among the 9 postulates which is proved as wrong later. No intermolecular force. This postulate is proved as wrong later. Let's check the other also. Molecules can be considered as rigid hard spheres. It is correct. The molecules are in random motion. It's also correct. Collisions are perfectly elastic. It's also correct. Then the wrong postulate among the 9, which is proved as wrong later, is first choice. A choice is the correct answer. Therefore, question number 5, the correct answer is A. Question number 6, it's about the number of degrees of freedom. Already explained the first 2 questions. Even then, once again, I will explain. Number of degrees of freedom for a diatomic gas. The number of independent variables or coordinates to locate a system or to locate a thermodynamic system. That's called degree of freedom. For monatomic gas, 3 degrees of freedom. Only 3 translational coordinates are permitted. For a diatomic gas, totally 5 degrees of freedom. 3 translational coordinates and 2 rotational coordinates are permitted. While for a triatomic gas, 6 degrees of freedom normally, 3 translational and 3 rotational coordinates are permitted. Here, the number of degrees of freedom for a diatomic gas is, for a diatomic gas, totally there are 5 degrees of freedom, 3 translational and 2 rotational. Therefore, the correct choice is B. Question number 7. Question is about RMS velocity. Using the postulates of kinetic theory, we have some equations. The kinetic energy of 1 mole of an ideal gas is 3 by 2 RT. Similarly, for expression for the RMS velocity is CRMS. Yes, 2 equations are there. Root of 3 RT by M and root of 3P by rho. P is the pressure, rho is the density of the gas. Here an important question is, there is a chance for an important question. If the gas is compressed by which the pressure is increased, what happens to the RMS velocity? If the gas is compressed and consequently the pressure is increased, the density of the gas will also increase such that P by rho is always a constant. Therefore, if the pressure is increased by compression of the system of gas, RMS velocity remains unchanged. It's an important point to be noted. Here, 2 expressions for RMS velocity, 3RT by M, root of 3RT by M, also root of 3P by rho. But here also equipartition theorem is applicable. Here the question is, temperature at which the RMS velocity of oxygen becomes equal to that of helium at 27 degrees Celsius. Helium is monatomic gas and oxygen is diatomic gas. Therefore, equipartition According to equipartition theorem, for diatomic gas, 3 becomes 5. Then here the substitution becomes RMS velocity of oxygen becomes equal to that of helium at 27 degrees Celsius. Helium is monoatomic. Therefore, 3RT. Helium at 27 degrees Celsius. Capital T is temperature in Kelvin. Therefore, 300 Kelvin divided by molecular mass helium. 4 gram means 0.004 root of 3 RT by M equal to root of 5 RT. For oxygen is a diatomic gas. It has 5 degrees of freedom. Therefore, the expression for the RMS velocity becomes root of 5 RT by M, and the expression for the kinetic energy becomes 5 by 2 RT. Here, root of 5 RT by M. 5 R, temperature is unknown. Instead of molecular mass, 0.032 gram. Now, solving, we get the result as 1440 Kelvin, capital T equal to. Therefore, here the correct answer is D choice, 1440 Kelvin. Question number 8. This is about Stefan's law of radiation. First, I will explain what is Stefan's law. The radiant emittance of a perfectly black body is proportional to the fourth power of the absolute temperature. Then what is radiant emittance? The energy radiated from unit area in unit time. The energy radiated from unit area in unit time. This is called radiant emittance or emissive power. Now, the ratio of the radiant emittance of the given body to that of a black body is called relative emittance or emissivity. Now, the Stefan's law is the radiant emittance of a perfectly black body will be proportional to the fourth power of the absolute temperature. That is, energy radiated from unit area in unit time is proportional to, then equal to a constant into fourth power of the absolute temperature. Radiant emittance of a perfectly black body is proportional to the fourth power of the absolute temperature. This proportionality constant sigma is called Stefan's constant. Its value is 5.67 into 10 raised to minus 8 watt per meter square per Kelvin raised to 4. This is the value of Stefan's constant. If the given body is not a black body, then also Stefan's law is applicable, but with a correction factor like the radiant emittance of a perfectly black body equal to sigma E T raised to 4, where T is the absolute temperature, E is the emissivity. That is, Stefan's law is applicable to all bodies, but for perfectly black body, the value of E becomes 1, then Re equal to sigma T raised to 4. For other bodies, the expression becomes Re equal to sigma E T raised to 4. For a perfectly black body, the value of E is 1. Now, the question is, at 27 degrees Celsius, the energy radiated is capital E. Then what will be the energy radiated at 627 degrees Celsius? Let's do the problem. E proportional to fourth power of the absolute temperature. Then E1 by E2 equal to T1 by T2 raised to 4. Then E1 is given as E, E2 is unknown, it is to be identified. T1 is 300 Kelvin. Then T2 627 means plus 273. Then 900 Kelvin raised to 4. Therefore, E here it becomes 3 times. 3 raised to 4, 81. Therefore, E2 equal to 81E. Therefore, the correct answer to this question is 81E. That's D choice is the correct answer. Next question is about Newton's law of cooling. Actually, for thermal radiation, several rules and laws are there. Stefan's law, Stefan-Boltzmann law, Wein's displacement law, Newton's law of cooling, Kirchhoff's law of radiation, and Planck's quantum theory of radiation. Actually, Planck's quantum theory of radiation, quantum theory originated for black body radiation. All these laws are for applicable to black body radiation. Now, Newton's law of cooling, what is it? The energy radiated from, or the rate of loss of heat from a hot body, the rate of loss of heat from a hot body will be proportional to the excess of temperature between the body and the surroundings, provided the temperature excess is small, applicable to the temperature under observing conditions. Not about sun's temperature, solar radius originating 6000 Kelvin. It's not applicable to such very high temperatures. Only for small excess of temperatures, Newton's law of cooling is applicable. I will explain once again. The rate of loss of heat from a hot body will be proportional to the excess of temperature between the body and the surroundings, provided the temperature excess is small. Now, here the question number 9 is, body cools from 80 to 60 degrees Celsius within 4 minutes. 80 degrees Celsius to 60 degrees Celsius. The time interval needed to cool the same body from 40 degrees Celsius to 30 degrees Celsius. What is Newton's law of cooling? Rate of loss of heat by time will be proportional to the excess of temperature between the body and the surroundings for small excess of temperature. In the first given data, cools from 80 degrees Celsius to 60 degrees Celsius within 4 minutes. Then the expression becomes d theta by dt. Only the temperature is changing. D theta by dt equal to k into theta 1 minus theta 2. 80 to 60, then d theta is 20. 4 minutes, we will substitute in minute itself. Answer will be obtaining in minute. Equal to k, theta 1 body temperature, theta 2 surrounding temperature. Body temperature means it is cooling, exposed, means temperature changes at each instant, and in such a case the average value of the body is to be taken. 80 to 60 means the average value is 70. Body temperature is taken as 70. Then theta 2 surrounding temperature, the room temperature is given as 20 degrees Celsius. 20. Now in the second case, the same body is cooling. The time interval needed to cool from 40 to 30. Now d theta is 10. Time interval needed is the unknown. Okay, 40 to 30 means 35, average value of body temperature, minus room temperature is 20 itself. Dividing here, it becomes 5 equal to k into 70 minus 20, 50. Then second one is 10 by t equal to k into 15. Dividing equation 1 by 2, we get the answer as 6.6 minutes. Here the correct choice for the question number 9 is C. 6.6 minutes is the correct answer. Now question number 10. The concept of temperature is a contribution of dash. Actually the answer is zeroth law. I will explain what is zeroth law. If two thermodynamic systems are thermally isolated from outside. If three separate thermodynamic systems are thermally isolated from outside, then if two thermodynamic systems are separately in thermal equilibrium with a third one, the two will also be in thermal equilibrium with each other. And two systems to be in thermal equilibrium, an unknown coordinate should be the same for both, and that is later termed as temperature. What is zeroth law? If two thermodynamic systems are separately in thermal equilibrium with a third one, the two will also be in thermal equilibrium with each other. And the concept of temperature is a contribution of zeroth law. Here the question is, the concept of temperature is a contribution of dash. Zeroth law of thermodynamics. I give the statement of that zeroth law also. Then other choices are second law. Second law is also you have to study. Second law also in physics and chemistry. What is second law? Second law of thermodynamics. Before that, first law. What is first law? First of all, you know it satisfies the conservation of energy. Zeroth law already over. Now first law. Every thermodynamic system has a variable called internal energy, whose change in a thermodynamic process is equal to the difference between the heat energy entering the system and the external work done. du equal to dq minus dw. That is first law. Zeroth law, the contribution of temperature, concept of temperature is a contribution of zeroth law. Similarly, the concept of internal energy is a contribution of first law. First law satisfies the conservation of energy also. Now, here the question is about zeroth law. Then the concept of temperature is a contribution of dash. Therefore, the answer is zeroth law of thermodynamics. The correct choice is C. Now, question number 11. For an isothermal process, the expression for the first law of thermodynamics becomes, first law, the statement I have already given. Every thermodynamic system has a variable called internal energy, whose total change in a thermodynamic process, change in internal energy du, is equal to the difference between the heat energy entering the system and the external work done, or dq minus pdv. This is first law, and internal energy is a contribution of first law of thermodynamics, and in first law the conservation of energy is satisfied. For an isothermal process, that is if the temperature is a constant, internal energy will be a constant, therefore du will be 0. Therefore, dq equal to dw for an isothermal process. For an adiabatic process, dq will be 0, then du plus dw. du plus dw equal to 0. This is for an isothermal process. This is for an adiabatic process. Here, in an isothermal process, the expression for the first law, original expression is du equal to dq minus pdv or dq minus dw. For an isothermal process, du becomes 0 or u becomes a constant. Then dq equal to dw or dq equal to pdv. Therefore, to this question, the correct answer is A, dq equal to pdv. dq, that's correct. Then second one, du equal to pdv. It is also, it's not correct. du for an isothermal process is 0. Therefore, du 0, then dq equal to dw. Therefore, C choice, du equal to 0. It is also correct. dq equal to pdv, correct. Similarly, du equal to 0. U is a constant, therefore du equal to 0. Now the last choices, A and C are correct. A and C are correct. Therefore, to question number 11, the correct answer is D. That is first choice and third choice are correct. Therefore, D choice is the correct answer. Question number 12. Which is not applicable to thermal radiation? Let us check one by one. Let's go through one by one. First one is Planck's quantum theory. It originated for black body radiation. Energy is emitted or absorbed in the form of discrete packets called quanta, whose smallest unit is a photon. The energy of a photon will be proportional to its frequency. E is equal to h nu. This is Planck's quantum theory. And according to Planck's quantum theory, energy of a radiation is always quantized. Now, second one, Stefan's law. Already we have mentioned the radiant emittance of a perfectly black body is proportional to the fourth power of the absolute temperature. It is also applicable to radiation. Then, Weidmann's law. What is it? The ratio of the thermal conductivity to the electrical conductivity will be a constant for all metals at a given temperature. This is Weidmann's law, applicable to the conduction, not for radiation. Now, Kirchhoff's law, there is a law for there is one Kirchhoff's law of radiation in the case of black body radiation. That is, the ratio of the emissive power to the absorptive power is a constant for all bodies at a given temperature and will be equal to the emissive power of the black body at that temperature. Here, first choice is applicable to Planck's quantum theory is applicable to radiation. Stefan's law is applicable to radiation, but Weidmann's law is applicable to conduction. Here the question is, which one is not applicable to radiation? Weidmann's law is applicable to conduction. All the other three laws are applicable to radiation. Therefore, the correct choice is C. Let's go to question number 13. Among the practically existing engines, which has the maximum efficiency? Earlier, we mentioned about Carnot's engine. It is an idealized heat engine which can never be made practical. All conditions are ideal. Now, some practically existing engines are also there. One, steam engine or Rankine engine, because steam engine follows Rankine cycle. For steam engine, the maximum possible efficiency is 32%. Then, petrol engine or Otto engine. Petrol engine follows Otto cycle, OT2U. Here the maximum possible efficiency is only 52%. Then diesel engine, it follows diesel cycle. The maximum possible efficiency is 63%. Among the practically existing engines, the maximum efficiency is for diesel engine. It has very high power output. Then maximum efficiency up to 63%. Here the question is, among the practically existing engines, which has the maximum efficiency? Steam engine, no, it has only 32%. Rankine engine, it is one and the same. Then a steam engine is also known as Rankine engine because it follows Rankine cycle. Then diesel engine, 63% maximum possible efficiency. That's the answer here. Then Otto engine, it is another term of petrol engine. Petrol engine follows Otto cycle. It has the maximum efficiency up to 52%. Here, therefore, the answer is among the practically existing engines, which has the maximum efficiency. Steam engine, Rankine engine. Rankine engine means Rankine engine means steam engine, another term of steam engine. Then diesel engine has the maximum efficiency. Otto engine means petrol engine. Petrol engine follows Otto cycle. Therefore, the correct choice to this question is C. Diesel engine is the answer. Question number 14. The question is it's a direct question about a formula. For an adiabatic process, the expression for the work is, for an isothermal process, the work is 2.303 nRT log V2 by V1. For an adiabatic process, for 1 mole, W equal to R by gamma minus 1 into T1 minus T2. But gamma is Cp by Cv. Therefore, W equal to Cp by Cv minus 1. Then Cv comes at the top. Cv into at the denominator Cp minus Cv, and Cp minus Cv is equal to R. Therefore, Cv into T1 minus T2. These two are the expressions for the work done in an adiabatic process. This is the expression for an isothermal process. R by gamma minus 1, where gamma equal to Cp by Cv, ratio of specific heats. T1 minus T2, that's a correct choice. Cv into T1 minus T2, that's also correct. Therefore, the correct answer to this question is B and C are correct. That is, D choice is the correct answer. Now, question number 15. It's a question from the session oscillator. not from heat and thermodynamics. The time interval needed for an oscillator to cover 1/8 of an oscillation. In the case of an oscillator, the displacement from the mean position is given by y equal to a sine omega t. The time interval needed for an oscillator to cover 1/8 of an oscillation. Let's check it. Suppose a pendulum is taken as an oscillator. Now, one complete oscillation means starts from the mean position, reaches the extreme position, reaches the mean position, again reaches the extreme position, then to the mean position. Now, it completes one oscillation. Therefore, for 1/4 of an oscillation, the displacement is this much, that is amplitude. For 1/8 of an oscillation, the displacement is half the amplitude. Therefore, y equal to a by 2 equal to a sine omega. Omega is 2 pi by time period into t. And sine function becomes half if 2 pi t by t is equal to 30 degree or pi by 6. Therefore, 2 pi t by capital T, where capital T is the time period of oscillation, equal to pi by 6 or 30 degree, pi by 6 radian. Now, the time interval, time is 2 into 6, 12, or t by capital T divided by 12. The time interval needed to cover 1/8 of an oscillation, the correct answer is time period divided by 12, that is t by 12. A choice is the correct answer. You remember one thing, corresponding to 1/8 of an oscillation, the value of displacement is half the amplitude, and I substituted that value here. Therefore, the correct choice is A. Question number 16. The displacements of an oscillator corresponding to the velocities. Two velocities are given, two displacements are given, and the amplitude of oscillation we have to identify. The expression connecting these terms are velocity v is equal to omega root of a square minus y square. The vertical velocity of the oscillator, omega angular frequency or angular velocity, amplitude of oscillation, displacement at the considering instant. Therefore, v square equal to omega square into a square minus y square. The displacements of an oscillator corresponding to the velocities 2 meters per second and 1 meter per second are 5 centimeter and 10 centimeter respectively. Velocities 2 meter per second and 1 meter. First case for 2 square and converting into CGS system, because displacements are given in centimeter into 10 raised to 4 meter per second. Omega square a square minus displacements are 1 meter per second. Displacements are 5 centimeter and 10 centimeter. Therefore, first displacement 25 y square. In the second case, velocity is 1 meter per second. Squaring 1 square 10 raised to 4 centimeter per second, converting equal to omega square into a square minus the displacement is now 10 centimeter, then squaring 100. Dividing, we get the value of A as root of 125 or 5 root 5. Therefore, here, the answer to this question is 5 root 5 or root of 125. D choice is the correct answer. Question number 17. An interesting question, but very simple. The frequency of an oscillator is F. Frequency of its KE will be dashed. Several times this question was asked for different exams. Now, an oscillator, this is the mean position. Then, this covers one oscillation when it covers this much of distance, one cycle. Therefore, in an oscillator, in the case of an oscillator, during its oscillation, at the mean position, the kinetic energy will be the maximum, and at the extreme position, kinetic energy will be zero, or the potential energy will be the maximum. Means the kinetic energy will have the maximum value at the mean position. Now, during one complete cycle of oscillation, it intersects or it passes through the mean position or K peak point twice per cycle. Therefore, if the frequency of oscillation of the oscillator is F, the frequency of the kinetic energy means how many times it passes through that K peak point, the mean position, is 2F. If the frequency of oscillation is F, the frequency of K peak point, that is the frequency of kinetic energy, will be 2F. That is the meaning of the question. Therefore, if the frequency of oscillation of an oscillator is F, the frequency of K will be 2F. Means per cycle 2 times it go through the K peak point. Answer to this question is B choice. 2F is the answer. Now, the question is about the vibrations of air column. If a tuning fork is made excited and is brought near the mouth of an organ pipe which is dipped in water, then the system can act as a closed tube. Organ pipe can act as a closed tube if it is immersed in water. If an excited fork is brought near the mouth of an organ pipe, the air column inside will vibrate. If the air column length is gradually increased for a particular minimum length, the sound of vibration becomes the maximum. Then the vibrating air column and the excited tuning fork will have the same frequency, or the two are said to be in resonance, corresponding to the first resonating length for a closed tube. An organ pipe dipped in water can act as a closed tube. In the case of a closed tube, corresponding to the first resonating length, the air column length will be equal to lambda by 4. Then 4L equal to lambda, the wavelength, and the fundamental frequency V by lambda is given by V by 4L in the case of a closed tube. And for an open tube, it becomes, open tube means both the ends are left open. Then the fundamental frequency is V by 2L. In the given question, the fundamental frequency of vibration of an air column in an open tube is F. Fundamental frequency V by 2L. In the case of an open tube, it is given as F. Now, half length is immersed in water. If half of its length is immersed in water, now it can act as a closed tube. And the formula becomes V by 4L, but the length of the air column is half of the initial length, that of the open air column. Therefore, here air column length is L by 2 if half length is immersed. Now, what will be the frequency? Here V by 2L equal to F. Here formula is V by 4L, but the value of L becomes L by 2. Therefore, it becomes V by 2L itself. Therefore, it is also F. That is, if an open tube is immersed in water and half of its length is exactly immersed, the fundamental frequency remains unchanged, F itself. Therefore, if the half length is immersed in water, the frequency becomes F itself. That is, C choice is the correct answer. Question number 19. About seconds pendulum. Generally, the time period of oscillation of a simple pendulum is time period equal to 2 pi root of L by G. And for a seconds pendulum, T equal to 2 seconds. Time period of oscillation will be 2 seconds. Here 2 pi root of L by G. If this same system is brought to moon surface, same pendulum is brought to moon surface, there the G value is 1/6 of the G value on Earth's surface. Therefore, at moon surface, the expression becomes 2 pi root of L by G by 6. G value is only 1/6 of its value on Earth's surface. Therefore, the time period of oscillation at moon surface will be, on Earth's surface it is 2, and if it is 2 on Earth's surface, at the moon surface it becomes 2 root 6. This 6 comes at the numerator. Therefore, the time period of oscillation at the moon surface will be equal to 2 root 6. Therefore, the correct choice to this question is 2 root 6 second. D choice is the correct answer. Question number 20. We have to identify the statement. The statement is, no engine operating between any two temperatures can be more efficient than a Carnot engine operating between the same two temperatures. Actually, this is the statement of Carnot's theorem. But let us check. Let's go through one by one. First choice is first law of thermodynamics. We mentioned every du equal to dq minus dw. That is first law of thermodynamics. Second law has two statements, closure statement and Kelvin statement. What is Kelvin statement? It is impossible to get a continuous supply of work by cooling a body below the coldest of the surroundings. It's just a statement. Here the choices are, first choice is first law of thermodynamics. Every thermodynamic system possesses a variable called internal energy, whose change in a process is equal to the difference between the heat energy entering the system and the external work done. Then second law of thermodynamics, no. Then third one, Carnot's theorem. It is directly given in the statement. No engine operating between any two temperatures can be more efficient than a Carnot engine. Therefore, here the statement is directly given, and we have to identify the statement, not the first law of thermodynamics, not the second law of thermodynamics. Second law means closure statement and Kelvin statement. Carnot's theorem. Actually, it is the statement of Carnot theorem. Kelvin statement is included in the second law of thermodynamics. Therefore, to the question number 20, to the given question, the correct answer is C choice. C choice is the correct answer to the question number 20. Question number 21. Here also a statement is given. It's impossible to get a continuous supply of work by cooling a body below the coldest of the surroundings. This is, in the previous question, we discussed several statements. Second law has two statements, closure statement and Kelvin statement. What is closure statement? For a self-acting machine unaided by any external agency, it's impossible to transfer heat from a body at a lower temperature to that at a higher temperature. This is closure statement. For a self-acting machine unaided by any external agency, it's impossible to transfer heat from a body at a lower temperature to that at a higher temperature. That is one of the statements of second law of thermodynamics called closure statement. Then Kelvin statement. It's impossible to get a continuous supply of work by cooling a body below the coldest of the surroundings. That is Kelvin statement, second part of second law of thermodynamics. Now, here the question is, it's impossible to get a continuous supply of work by cooling a body below the coldest of the surroundings. That is Kelvin statement of second law of thermodynamics. Kelvin statement of second law. Both the closure statement and Kelvin statement belong to second law, but this statement is Kelvin statement. Therefore, B choice is the correct answer to this question. Now, question number 22. The concept of internal energy is a contribution of. That's also mentioned earlier. Concept of temperature is introduced by zeroth law. concept of internal energy is a contribution of first law of thermodynamics. Here the answer is first law of thermodynamics. Internal energy is a contribution of first law. That is to question number 22. The correct answer is B choice. Now, question number 23. For an adiabatic process, the expression for the first law becomes, I will write the expression of first law, general expression for the first law. du, change in internal energy, equal to the difference between the heat energy entering the system and the external work done. For an adiabatic process, it's a thermodynamic process in which no heat energy enters or leaves the system, or enthalpy of the system remains unchanged, or Q is a constant, or dQ is 0. Therefore, for an adiabatic process, dQ is 0. Then du plus dW equal to 0, or du plus pdV equal to 0. These are the representations of first law for an adiabatic process. For an adiabatic process, the expression for the first law becomes du plus pdV equal to 0. That's a correct choice. dQ equal to pdV, no, dQ equal to 0. du equal to 0, no, it is for isothermal process. du equal to dQ. du it is also wrong. Therefore, the correct answer to this question is A. Now, question number 24. The SI unit of specific heat capacity. What is specific heat capacity? Heat required to raise the temperature of unit mass of a substance through 1 Kelvin. Heat required to raise the temperature of unit mass of a substance through 1 Kelvin. Heat per unit mass per degree rise of temperature. Rise of temperature. Therefore, SI unit becomes joule per kilogram per degree rise of temperature per Kelvin. That is joule per kilogram per Kelvin, or joule per kilogram per Kelvin. This is the SI unit of specific heat capacity. Joule per kilogram per Kelvin. Direct question, only the unit is asked here. Therefore, to question number 24, C choice is the correct answer. This is the last question of this session. The specific latent heat of steamers. What is specific latent heat? The term latent heat exists only in the case of state conversion without any temperature change. Example, melting of ice, or freezing of ice, freezing of water to ice, or vaporization or condensation. Under the atmospheric conditions at 100 degrees Celsius, water boils and will be at the same temperature, it will be converted to steam. Then specific latent heat of fusion or vaporization. Specific latent heat is the heat required for the state conversion of unit mass of a substance. State conversion of unit mass of a substance. Then, example, specific latent heat of fusion of ice, 80 calorie per gram, or 336 into 10 raised to 3 joule per kilogram. Then, specific latent heat of steam, or specific latent heat of vaporization, 2268 into 10 raised to 3 joule per kilogram, or 540 calorie per gram. Here, the specific latent heat of steam is either 540 calorie per gram or 2268 into 10 raised to 3 joule per kilogram. Therefore, here the answer is 2268 into 10 raised to 3 joule per kilogram. Today, we have discussed several questions from heat and thermodynamics, including the kinetic theory of gases, and a very few questions from small quantity of questions, small number of questions from waves and oscillations. All the question. All the units are highly problematic sections. Go through all the questions, and this is the last unit of our exam series for the 11th standard, and waves and oscillation, that's the last topic of 11th standard. Therefore, after finishing these topics also, directly we will be going to the school exam or board exam, etc. Anyway, this is the last units. This is the last unit of 11th standard, and I wish you all the best for the exam. Wish you all the best. Thank you.